All right, so today we're finishing it up, chapter 12, doing it in one day. So, last lecture of the year, that's pretty exciting. It's exciting. I hope it's as exciting for you as it is for me. Let's get weird. All right. So, chapter 12 is all about creating these like regression models. So the idea here is, like we're going to get some data from making some measurements in the real world. We're going to take that data, and we're going to use our calculator to do this, to generate what's called a regression equation. And there's going to be 6 different types of regression equations that we're going to be responsible for. So like there's linear regression. So that's just like a y equals mx plus b equation. There's quadratic regressions. There's cubic regressions. We have exponential. There's logarithmic. I think it's this. What just happened there? That was weird. And then there's power. Okay, so we have these 6 different types of regression equations. The question really becomes, which one of these would you want to use in a given situation? So one way that we might want to make our decision is by looking at the scatter plot. So when I say scatter plot of the data, what is a scatter plot really? It's plotting the data like points, like x's and y's, right? So if we're looking for something that's linear, what's the scatter plot going to look like? Like a line, right? Yeah, sure. And what's a quadratic going to look like? Parabola. Yeah. And you guys get that these scatter plots that I'm just sketching are just examples, right? There's lots of different ways that parabola could be opening up or down or whatever, right? Cubic is going to have like 2 bends to it. An exponential, kind of looks like that hyperbola shape. That's the name for that shape of a graph. Logarithmic is going to look like that. And a power function, just this kind of varies, right? And the reason that we can't really kind of say, oh, the powers are all going to be one shape, is if you look at the power function, the exponent is going to depend on the data, right? So it could be something that resembles a quadratic, or it could be something that resembles a square root function, or it could be lots of different things. It's a pretty versatile model. Everybody's cool with that? Okay. So let's take a look at a specific example and kind of talk through doing this, right? Is that okay? It's just there it comes. Took forever there to. So here's a perspective data set, and if we're going to try to create pick which kind of regression we want to make, the natural first step would be to look at the scatter plot. So we're going to use our calculator to do that. I would never ask you to plot something this detailed by hand. If you have your calculator with you and you'd like to follow along, I would encourage you to do so. If you prefer to just sit and watch, that's perfectly fine. Just make note that, the video is here, and if you need the calculator help, that's a great place to go back to. So before we can start creating this scatter plot, we got to enter this data into our calculator. So to enter data into your calculator, you're going to press the Stat button, which is right here in the middle. And then from the Edit tab, we're going to select the Edit command. And now I have this data already typed in here. Some of you guys, probably this is blank. Some of you have data already there. If you already have data there, you have a couple of options on how to get rid of it. You can delete individual entries one at a time with the delete key. So if I want to get rid of the 12, I can just press delete and it'll delete the 12. Or if you have a whole column of data that you don't want anymore, you can move your cursor so that it's on the name of the column and then press the clear button, not delete, and then the down arrow and it'll wipe the entire column for you. If you press the delete button there, it's going to get rid of that entire label for you, and it's kind of a pain in the butt to get back. So I encourage you to be careful about that and not delete the list, but just clear the list. If you do happen to make an oopsie, Mr. Kulik can help you fix it. Come see me, but in general, just be careful there. So I'll give you guys that are following along a couple minutes to type this stuff in, since I already had everything pre-typed in. I know I'm a little bit ahead of you. While we're waiting, I want to point out to you that while I'm doing this, I'd also want to make note of the names of the lists that I'm typing this data into. I type mine into L1 and L2. I assume that most of our calculators default is set where we're in L1 and L2, but if some of you've been in here before and you accidentally deleted a list or you put it somewhere else, that'll become important later on. So just make sure you're aware of where you put which data set. All right. Anybody still typing that needs a minute? Great. Okay, so now that we've got our data entered, we can go about making our scatter plot. So to make a scatter plot, we're going to press second and the y equals button. You're allowed to make up to 3 scatter plots at a time. We're only going to ever want to make 1 at a time, personally, for what we're doing. So I'm just going to select plot 1. The first thing I want to do is turn it on. So that option, I'll press enter to make sure the on is highlighted. Under types, the first option is the scatter plot type. That's the one we'll be using. And then the X list, if I look at my data set, from the way it's labeled, it's pretty clear that L is the independent variable and W of L would be the dependent variable. Right? It's very clear from the notation that that's how it should be set up. So I typed L into L1. So I'd want my X, my independent variable, to be L1 and my Y to be L2. Now, my calculator is defaulted that way. If yours was not defaulted that way, or you typed your data into a different location and need to change where it's at, I'd point out to you that above the numbers 1, 2, 3, 4, 5, and 6 in blue is a little L1, L2, L3, L4, etc. So if I needed this to be, say, L3, I could press second and the number 3, and I could change it to L3 if I needed to. Now, I don't, so I'm going to change it back to L1. But if you were somebody that, oh, I was missing L1 and L2, so I just used L3 and L4 to type in my data, or I have a bunch of problems that I've been kind of working on. I'm going to have one problem in one set and another problem in another problem, and I don't want to delete them out because I wasn't sure if I got the right answer, so I want to go back to it, but I don't want to have to retype the date. Whatever reason. And the last option here is the mark. I usually like the squares because I think they're the easiest to see. So that part doesn't really matter, but I like the squares. Okay. The next thing I need to do before I hit graph is I'm going to press the zoom button. Oops. I'm going to exit out and then press the zoom button. And I'm going to pick the zoom stat option. This way I don't have to worry about messing with my window, so I make sure I can see all my data. Oops. The zoom stat option will automatically adjust your window so that all of your X and Y's for your data fit inside the window. So it'll pick that window automatically so you can see all the data points that you're plotting with your scatter plot. So this is the shape that you should have gotten. Anybody have an issue getting their scatter plot to show up, or it looks dramatically different than what I have here? If you have one point that's like, oh, that didn't look like it's in the right spot, the likely issue is you typed the wrong number into when you entered the data. And so you just go back and double check to make sure that you typed all the numbers in correctly. If something looks like, well, looks way out of place. Okay, so looking at the shape, what do we think here? What model would you want to use? Okay, so Paul suggests exponential. Anybody disagree with that? What else might fit this well? Linear, okay, sure. Anybody else? You want to try a log? Sure. And Mr. Kulik says this kind of looks cubic to me. It looks like there's almost two bends starting on that. So, okay. Well, those all seem like reasonable guesses based on this. Mr. Kulik, could we do something better than just guessing on which one of these might be the best one? Yeah, actually we can. So there's two kind of numeric ways to see which regression is going to be the better of, or is going to be better, or a way to measure how well it fits the data. So there's two of those measurements. The first kind is the correlation coefficient. And we abbreviate that with the letter R. And basically what this is it describes how linear the data is. And this correlation coefficient exists on a continuum between -1 and +1. So at 0, we'd say like there's no linear relationship here. Now 0 is kind of a theoretical value. I don't know in practice you'd ever see any data set having a correlation coefficient value of 0. You'd need something that was like perfectly random across the entire, like xy axis, which is kind of impossible to generate. So if the value is -1, what that means is the data is perfectly linear, but the slope is negative. By perfectly linear, I mean there's a line that exists that passes through every single point of the data. Everybody's okay with that idea? And +1 is the same thing, except the slope is positive. So we can say then basically as the absolute value of r approaches 1, the data is more linear. Now, this correlation coefficient is really only appropriate when dealing with linear data, which is not super helpful to us because we're considering a whole bunch of non-linear models here. So our other option that'll be more practical for us is called the coefficient of determination. And that's r squared. And basically, this is going to describe the fit of a regression equation to a data set. Now, r squared exists on a continuum from 0 to 1, where 0, again, is kind of a theoretical value, where you have no fit at all the way to 1, which is like a perfect fit. And by that, I mean the points in your data set would actually be points, would all be points on your regression equation. Okay with that idea? Okay. Notice that in either of these situations that I described to you how we're actually going to calculate these. I did not. Why did I not do that? Because the calculator is going to do it for us, which is lovely, right? It's beyond the scope of this class to talk about how these things are actually computed. We're just going to let the computer do it, or the calculator do it, and we're just going to be responsible for like interpreting the results. Feel good? Okay, so let's talk about how we make a regression equation on our calculator. So we're actually going to make 4 of them for each of the 4 suggestions here. We're going to do an exponential, and then a linear, and then a logarithmic, then a cubic. Everybody's cool with that? All right, so to get a regression equation, we're going to press the stat button. Then we're going to move to the Calculate tab. And if we look at this list, this is where all of our regression equations live. So there's the linear regression, quadratic regression, cubic regression, quartic, that's a degree 4 polynomial. We're not going to worry about that. Another linear version, I don't know why they felt it was necessary to have like where A was the coefficient and B was the constant, and another version where A is the constant and B is the coefficient. I don't know. I always just use the first one. ln reg is our logarithmic. So again, with the logarithmic regression, we're always going to be using the natural log as our logarithm of choice. So ln reg is for logarithmic. Exponential regression, power regression, logistic we're not going to deal with, even though we know what those are. There's a sinusoidal regression where it can create a sine function for us. We're not going to deal with that either. And then a manual fit option that we don't care about. So our first suggestion was exponential regression. So let's pick the exponential reg. Now I typed my x data into L1 and my y data into L2. So that's fine there. If yours are located somewhere else, you would need to update where those are located. The frequency list will always be blank for us when we're doing this, so don't worry about that. The next option is to store the regression equation. I'm going to choose to do that. What this is going to do is the calculator is going to save the actual equation someplace for us so we can use it later on. The natural place you'd want to do this is into the y equals menu, so you can go back and use that equation later on to graph or to evaluate. So I'm going to save this one into y1. To get the y1, we press vars, we go over to yvars, and we pick the function option, and then we'll pick y1. And then we'll hit calculate. How many of you did not get the r or r squared values to come up when you did this? Okay, probably a lot of us, right? Those of you that didn't have a calculator with you or that are going to have to do this later, keep in mind what we're about to do, because the default on most of our calculators is that these are not set to come up. So let's talk about how we turn that on. Once you've turned on the r and r squared values, they'll come up from there on out. You don't have to do it again, unless like your batteries die or your calculator memory gets reset or something like that. Okay? So the option that we're looking for to turn on those r squared and r values is called Diagnostic on. The easiest place to find that is by pressing second and then the 0 button. This opens up the catalog. The catalog is just a list of every single operation on the calculator in alphabetical order. Now, we could start scrolling, but we'd have to scroll all the way down through the A's, the B's, the C's, to the D's. Or, if you notice above some of the buttons on your calculator is a little green letter like A, B, C, D, E, F. So if I press this x to the negative 1 button where the D is above it, it'll skip me all the way down to the D's. Save me some scrolling. And I'm going to scroll till I find this one that says Diagnostic on. Okay. Once you've found that option, go ahead and press enter, and that'll paste it onto your home screen. If you press enter again, diagnostics are now on. Should say done. So if you press second and enter twice, and then press enter again, that'll rerun the regression that we just set up a moment ago, and now your r and r squared should show up for you. Everybody okay there? So I'm just going to write down my r squared value for this. Well, through 4 decimal places, I guess. Just so we can see which one ends up being the better of the 4 that we've suggested. Everybody's cool so far? Okay. I'm going to go back and do another regression equation, this time for a linear. So stat, go to calc, scroll down to linreg. I'm going to do L1 and L2, and this time I'm going to store this into Y2. So I can do something with all these different functions later on. Because I don't know right now which one's going to be the better one. So that's 0.9289. So right now that's slightly better than the exponential. Everybody see that? Because the r squared is a little bit closer to 1. Okay, I'm going to now go ahead and do the logarithmic one. So I'll press stat, go over to calc, scroll down till I find the ln reg. And this one I'm going to store into L3, or Y3, excuse me. So I calculate again. Here the r squared is 7704. That's not so good. And then the last suggestion was the cubic. So again, stat, calc, cubic reg, and I'll store this one into Y4. And there my R squared is 0.9905. Everybody feels okay with what we've done here? Again, the calculator is doing all the heavy lifting for us. Our job is just kind of thinking about what's going on and interpreting the results. Of these options, the cubic is the best fit, right? And now that makes sense because the data we're given here has no context to it. But what if we attach some context to it? What if this data, what it is, it's measuring the length of an organism and then the weight for that organism? Okay with that idea? So we've just attached now, so this data means something now. It's not just a collection of meaningless numbers. Does a cubic function seem like that would have any realistic, like does that realistically fit what's going on here? Doesn't seem like it, right? It doesn't seem like there should be a cubic relationship between weight and length of an organism. Like, that's weird. So even though that's the best fit to the data, it may not be the most realistic model for this. And we'll see some reasons here later on why that might become unrealistic later. What might be a more realistic model here? Of the options we've looked at, what might be the most realistic? I would think the linear, honestly, right? That feels like, you know, things is pretty much a 1-to-1, like every inch is like 10 more pounds of weight or something for a human. Is not an unfair estimate for like an average human being. I would think that the, you know, a similar thing would hold for whatever organism we're looking at. All right, just to give you an idea of what this is actually looking like, let's look at each one of these one at a time and compared to our scatter plot. So I'm just press the y equals button. I'm just unhighlighting all but one of the equal sign. So it's only going to graph one of these at a time for me. So the first one is the exponential. If I hit graph, here's my data set. Here's my exponential function coming through. And it does an okay job until kind of the very end where it seems like it's shooting off much faster. And if I do the next one, this is the linear one. So if I do that, so the linear is kind of bad in the beginning, but the longer it goes, it looks pretty good. We also looked at the logarithmic. This wasn't a very good fit. Let's look why. So you see that it's pretty far from the data in a lot of places, right? Particularly in the beginning, it's bad, and at the end, it's starting to get bad. Again, it looks, right? And then the last one was the cubic. Let's take a look at that. This one had a very good R squared value and has a very nice tight fit to the data set we have. But like I noticed in the beginning, apparently a shorter organism should weigh more, which doesn't seem real. So already I'm a little bit dubious about this actually being a realistically best model, even though it's an excellent fit to the data. Right? And this is one of the common problems when we create like a mathematical model for something. Do you just take the thing that has the very best fit, but maybe doesn't make a lot of sense as to why it would be a good fit? Or should we be thinking about like, okay, what in reality should be the relationship here? And let's create a model with that kind of relationship that fits as good as we can get, even if we sacrifice a little bit of fit for more realistic description here. So we've created these models, right? And we can do this really for any data set. What are we going to do with? Why are we creating a mathematical model? What are we going to do with this? What do we use these things for? We use them to make predictions, right? That's the point. So for example, maybe I want to find the weight for an organ, or predict what the weight for an organism that has length 58. Everybody okay there? So to do that, all I'm basically doing is plugging 58 into the model and seeing what the result is, right? The lovely part about the way we did this is we stored all those equations into the y equals menu. So if I wanted to plug 58 into the exponential, I can do y1 of 58. And the calculator is just going to take care of that for me. I don't have to write down the model again and plug it in and type in all those numbers. The calculator stored all the numbers for the equation for me already, and it just plugged it in for me automatically, and it's very nice and very efficient. So 27.7, we'll call that. So that's if I had the exponential. We did the linear in y2. So let's see what that gives us. Oops. So 34.2. And then y3 was the logarithmic. So there I get 33.8. And then what's probably our best prediction for this problem was using the cubic, which had the tightest fit there. So if I do that was in y4, that gives me 34, let's call that even. Everybody's okay there? So we have 4 predictions. Of these 4 predictions, which one do you think is the most reliable? Probably the cubic one, because it is the best fit for the data that we have. Now, if we had instead wanted to do, let's say we do W of 1,000. So we found some really long organism. Let's see what we get there. So, forget it. Look at that number. 3.2 times 10 to the 40th. That is one heavy son of a gun right there. Yeah, that's like, has its own gravity heavy. That doesn't seem very realistic. Let's see. So let's do the linear one. 893. Oh, that's... Oh, come on now, calculator. OneNote, I'm going to fight you.
You said this on multiple days.
I know, I'm going to digitize myself, go into the computer, and...
But isn't it just like code?
Yeah.
So how are you gonna,
Yeah.
you're gonna leave that to you?
Yeah, I'll find a way, don't worry. Now, I really... drives me nuts. Grrr.
What was that?
That's me getting angry. The internet. I don't know, my computer.
Your OneNote.
Yeah, that too. All of it. All these little ones and zeros. Okay, 115.1. And then let's see. The cubic we said was our best fit, right? Let's see what we get there. Oh, that's a joke. Well, that's just absurd now, right? Why is that patently crazy? Yeah, negative weight? Get out of here. That can't happen. If we looked at these, which one seems the most reasonable? Yeah, the linear one. So this is an example where the model that the function, the model type that kind of makes the most logical sense ends up giving us maybe the better estimate in this case. So this is actually two different types of prediction we've done here. This first situation we did, this was interpolation. So what that means is that the value that we're predicting lies inside the extremes of my data set. So like 58 was between 12 and 72, which were the ends of my data set. Okay? Anything that you pull or anything that you're predicting inside the extremes of your data set, the function or the regression equation with the best R squared value is probably going to give you the most reliable prediction. Right? Extrapolation is what we did over here. And this is where the value that we're predicting for lies outside of our data set. In this case, just because something had a great fit doesn't mean it's going to do a great job of predicting when we're outside of our data set, our data range. Everybody's okay with that idea? And I think this example really nicely illustrates it, right? We had one that had a crazy good fit, but when we start extrapolating with it, we get like bonkers nonsense answers. And then one of our regression equations that wasn't quite as good a fit, but was still pretty good when we get outside of our data set range, still appears to be giving us a pretty reasonable answer, right? So that's a example of like the two types of prediction that we might do. Okay? Everybody feel pretty good so far? Again, no difficult mathematics are being done. The difficult part is like using your noodle to kind of understand what's going on here, using some common sense and really understanding the situation and what are we really describing and all that kind of stuff. All right, we have one last thing to talk about. When predictions go wrong. So one example of a reason why a prediction might be unreliable is that you're using extrapolation. Inherently, extrapolation is unreliable because you're not sure that the mathematical model or the type of model you've chosen actually is a good descriptor for the physical behavior that you're measuring, right? Before, when talking about length and weights, we guessed that linear would be the most sensible relationship between, the length of an organism and its weight, but we don't really know. It just seemed like that would make sense. You know what I mean? So even our linear extrapolation is, I don't know, we're just guessing. Is everybody okay with that idea? Now, are all extrapolations going to be equally unreliable? This is just kind of an aside. Are all extrapolations equally unreliable? No. Okay. So for example, which one do you think would be more reliable if I wanted W of 75 or W of 1,000? 75. Why? It's closer to the extreme of my data set, right? And this is something that I think we probably experience on a daily basis. So there's a prediction that you probably look at almost every day that illustrates this example really nicely. Anybody can think of it? The weather, exactly. So you look at your weather app on your phone and you look at the weather for the next hour, that's probably going to be right. You look at the next day, often still pretty good. You go to the 10 days out or a week out or whatever that your app closes out at, it's probably pretty close. You look a year in the future what the weather's going to be like, who the heck knows, or 20 years or 30 years or 100 years in the future, really unreliable. Does that make sense, kind of what we're getting at? I think that's a really nice, easy to understand everyday example of what we're trying to talk about here. Okay. What's another reason why our prediction might not be reliable, or why our prediction might be really wrong? Well, you just have a bad fit, right? R squared is not close to 1, right? You have a model that just doesn't fit your data very well and use that to make predictions. Well, they say garbage in is garbage out, right? Okay. What's another reason?
Would an outlier affect it at all?
So I'm going to create a class of reasons here. I'm going to label these as bad data, one of which would be outliers. Present in data. Okay. So for an example of this might be, if we're taking height, we're trying to create a relationship between the height and weight of human beings, right? So we measure a bunch of people and we measure 10 people and one of them's a sumo wrestler, it's 5'10" and 600 pounds or something. I don't know what sumo wrestlers weigh. It's probably not 600 pounds, probably 400 pounds. But that's a huge outlier to what a normal 6-foot human being would be, right? And gonna really bend our model in a way that probably doesn't make it reliable, make for reliable predictions. So sure, outlier would be a good example. What else? What other kind of bad data situation could we run into?
Does bias data matter at all?
Yes. So for example, let's say we want to create a model that takes the age of a human being and predicts the height. And let's say the data the data measurements we go over to the elementary school, and we just take the heights and ages of the elementary school students. What's that gonna do? Why, though? Okay, so you're growing the most as a child, right? You'd expect, if we did this and you try to use those measurements and you try to predict the age of a 40-year-old man or a 40-year-old person, it might be 75 feet tall, right? Like you get some crazy number. It's like, well, that can't be. Everybody's cool with what we mean by biased data? Or if we take the problem and we create just an easier bias than that, we're just looking at like age and height for a human being, and maybe we just measure all men. We're on average, 4 or 5 inches taller than a woman, the average man and an average woman. So automatically, like, you're going to have bad predictions for heights for women because of that, because of the genetic difference there, or biological difference, or whatever. Everybody does that feel okay there?
Feels pretty okay.
Okay. What else? Trying to think if there's anything else. These are kind of the classical examples of reasons predictions go wrong.
Do you need like independence or anything like that?
No, because we're not talking about like a probability situation here. I know you're pulling all your AP stats buzzwords. Yeah. So that's because we're not doing any probabilities not involved in a regression.
And it doesn't matter like the amount of data you have.
That would be reasonable though. Yeah. So too little data would be a problem. Ideally, how many measurements would you like to have in a perfect world? All of them. We want every single measurement that's possible, right? I want to measure all of the human beings. I want to measure all of the organisms. I want to measure all of the whatevers. Now, is that realistic? No. But ideally, you'd want a representative sample, that is like, okay, if we're doing, ages and heights of human beings, I'd want, like all of the age ranges kind of represented, and several people inside of each of those age ranges, and probably an equal or proportional number of males and females matching, the proportion of male and female to the Earth population, and eliminating any like obvious outlier situations. Like somebody that's born with like a congenital defect and has no like leg below their knee or something, like that's a, like probably not somebody that you'd want to include in that kind of sample because they are a rare occurrence. Anyways, that feels like a good list. Could there be more things? Sure. I mean, there could just be like dumb systematic errors, like, like you measured something wrong, but so yeah, it feels like a wrap for me. That's about all we want to do with chapter 12. We gave you the big overview, which I think is kind of the fun way of approaching this. Is kind of an interesting topic because it feels like, oh yes, I can certainly see this being something important in like life, people, scientists or researchers or economists or, politicians or whoever, like being really interested in creating these models and using them to make decisions about like, what should I do? Everybody wants to try to see the future, tell the future. Cool. Any questions on any of this? All right.